So here you see the energy calculation results of the simulation. They are grouped in two rows of first final energy by energy use, so which energy use is provided by which energy source. Secondly, a overview of energy end use in three scenarios. So how would the district look like if we provided it with natural gas? How would it look like if we heated it with district heating? And then the final actual variation on how does it look like with a heat pump situation. Then we have a final energy supply situation on a monthly basis, how the energy is provided during the year. And then, so this is all about energy use and energy provided. The second row is on the actual assessment of the positive energy district balance, including mobility. So you can see here again 4 variations, and the last one has a positive energy balance or a net zero energy balance. The next thing is the state of the district storages, meaning both the energy storage in the thermal hull and thermal mass, as well as electric storages. And then we have the greenhouse gas emissions for the building operation and the mobility of the district. Below we also have a dynamic view of the energy flows that you can specify the time frame on. So now let's go through it one by one. First is the final energy by energy use, which shows the electricity for plug loads, heating, cooling, domestic hot water, as well as battery and electric vehicles, if there are any present in the district. All values are expressed as electricity kilowatt hours per square meter net floor area and year. So they are indicative and can be easily compared. And the bars show how the energy use is provided by the energy supplies in the district. So for example, here in plug loads, 18.3 kilowatt hours per square meter are provided by directly using the PV photovoltaics that are used in this grid. 6 kilowatt hours come from the battery. 2.6 kilowatt hours come from flexible grid use, so using plug loads when there is renewable overshoot and renewables in the grid. And the rest, 14, is provided by just regular grid electricity. You can see for heating, we need 10 kilowatt hours per square meter in year, because keep in mind this is a heat pump system, and even more than twice as much in cooling. You can see the difference between heating and cooling in terms of provided energy. So here, the cooling can be provided by electricity from the photovoltaics by 6.7 kilowatt hours, and we can even use 2.2 additional kilowatt hours of photovoltaics that we would not need to cool the building down to 26 degrees, but we can use it to cool it down to 24 degrees. We can use an additional 2.2. And what that means is we can increase the PV, as you can see here, by 2.2 and decrease the grid electricity that has a higher primary energy factor that we want to avoid. Also, the battery can be can be used much more in the summer. And if you compare this to the heating situation in winter, you see the difference, especially in the PV use. Because in winter, most of the PV is already used by plug loads, so for heating there's not a lot of electricity to go around, but in summertime for the cooling, of course, we have a much better situation. On the other hand, you see that the flexible grid use in cyan here is higher in winter because for the heating. This is mostly because the flexible grid use is mostly available in times of high wind power events, and these typically occur more frequently during the winter. You can also see how the battery is supplied with electricity. Mostly the battery is supplied with renewable grid electricity with flexible use, and a smaller part is also battery provided. So here the importance of the final energy by energy use diagram is to check whether the energy demands for plug loads, heating and cooling, a domestic hot water battery and EVs are reasonable and to be expected, and how they're supplied by the various energy sources. Next up, we have total energy end use in 3 variations. The first 2 are just indicative to show how much energy can be saved by switching to a heat pump based solution. Now let me just format this axis so that we can actually see the total amount. Yeah, so what you can see here is the amount of grid electricity in gray, the amount of photovoltaics that can be directly used or can be used in the district, then the natural gas that is required to heat, the district heating that is required, and for the heat pump system, this is already in the grid electricity. Now, only the heat pump solution has the potential to do grid supportive grid use because we are using electricity for the heating. And finally, you can see also how much photovoltaics we cannot use in the district and we need to feed into the grid. Now you can see that for the heat pump system, this value with 4.2 kilowatt hours per square meter net flow area and year is lower than the 8.5 that we would have to send to the grid for the natural gas and district heating system. So here you can see how much energy end use we can reduce by the heat pump system. And of course, what you can also do here is change the building type, the building construction, for example, the building envelope, and see how much more electricity you would need if you had different thermal insulation, for example. Let me just demonstrate this real quick here. So now we're at 140, around 140 energy end use. Now, what happens if I go up here to the walls and put maybe something like this? So these are more building code applicable U values, so not as efficient thermal hull. Now if I recalculate, again remember you need to recalculate so to see the effects, then you will see how much more the heating demand increases. You saw an increase in heating demand here, and also instead of the 140 that we had before, now we're almost up to 180 kilowatt hours. Now this is a way that you can check to see the effects of different thermal insulations. Let's switch that back to passive house and look at the next graph, or before that, let's recalculate here. Yeah, and you see again how the energy demand drops. Now the next result is the final energy supply of a monthly balance. So here you see how the district is provided with electricity throughout the year, and here you can see also how much energy demand is present at each month. So unsurprisingly, you have high peaks in the winter months for heating, but also for cooling in the summer months. What is important also is to see the effects of the photovoltaic direct use and the additional use of photovoltaics based on a flexible operation, the effects of grid supportive grid use, the effects that the battery is using. You can see the battery is mainly used in between the heating and cooling seasons. You can use the battery much more effectively. So all of these effects, again, you can have a look at what changes, for example, if we don't use flexible grid use, you can recalculate, and this means that basically the cyan bar here will vanish, and instead you use more grid electricity mostly, but sometimes also photovoltaic can play a larger role then. So here as well. Sometimes these diagrams don't update immediately. Sometimes it's even required to manually save if the recalculation does not have an effect on the district results. So these are the energy end use diagrams, and now let's come to the most important aspect, the positive energy district primary energy balance. And what you see here again is 4 different scenarios: natural gas, district heating, the heat pump system without flexibility, and final the actual assessment scenario with the final assessment scenario with can I not change this around? Okay, I cannot. Final assessment, heat pump with flexibility. Now, the difference here now is not very large because the flexibility provided from the grid is turned off. But basically what we have here is that we want to have this blue bar at least 0 or positive. If this blue bar, the primary N, is the primary energy balance, so it's the combination of the energy import that we need from the grid in terms of electricity, but here for this variation also natural gas, and for the district heating is also district heating. And this is the balance of the energy imports and the energy exports. The energy exports mostly being photovoltaics in yellow here, but also two aspects that are special to our assessment system. The first is the context of the density. As I explained earlier, highly dense districts do get a bonus here in their balance based on their density, and low dense districts get a negative bonus on their balance. Let me just show this real quick. We now have a 150,000 square meter district on a 40,000 square meter plot. This results to a very high density. What happens if instead of 40,000 we have 400,000 square meters, significantly reducing the density? We have a lot more space available in our district now, and this space could be used for photovoltaic generation, right? So if I change this, then you can see that the density context from being a positive energy balance factor from plus 40 drops down to a negative minus 60. So we actually need to produce even more electricity now that we have a district that has more space available. Now this means that it's more difficult now for less dense districts because they also have more space available to use more photovoltaics, right? Let's switch this back to 400,000. So this is the first impact. I now switched it back to a relatively high density district with a density space index, floor space index of around 3. So meaning that for each square meter of buildable plot area, we have 3 square meters of gross floor area. Then it's a positive here. And the second effect is the mobility budget that each district gets to supply its energy from renewable sources outside the district. Again, these are special to our assessment method that I showed earlier. If you don't want to use them, you can of course always take these out of the equation here and look at the energy balance without them and see if you have a positive energy balance then, if this is how you want to assess the energy balance. So this is one thing. Another thing is to keep in mind that the mobility energy here only is taking into account fossil mobility. So it does not show anything here because in this model that I have electric car share of 100%. So if I set this electric car share down to 0%, you will see that the energy import for the mobility is actually increased. And it's not a whole lot because I set this to a very low car travel district, but if I go to a more reasonable 5,000, you can see that the primary energy required for the mobility is actually much larger and can be as large as the energy required for the building operation. So this is why it's important to keep this into consideration and also think about mobility measures. So here you can see that all 4 of these variations, be it natural gas, district heating, heat pump, with or without flexibility, do not reach a positive energy balance and cannot be called a positive energy district. Now, what happens if I look at this in a dense urban environment with low car travels and 100% electric car share? Then let's recalculate and see. It is still not positive enough. Now what we can do is also include flexible grid use, because right now you see that we actually use more primary energy balance with flexibility than without. This is due to using the photovoltaics to overheat the buildings, which results in slightly higher heat losses. So this alone is actually detrimental. But if we also use the much higher potential of flexible grid use, you can see the cyan bar has reappeared here in our final energy balance, then we can actually achieve a positive energy balance. And then there is also a much larger difference between the heat pump system without flexibility and the heat pump system with flexibility. So these are the main ways to assess your district. You can now play around and change the specifications here. You can increase the photovoltaic system, you can increase the batteries, etc., and see what effect that has. Also, you can switch out basically all the parameters and see the effects of the resulting energy balance. Now, the primary energy balance is the main way to assess the primary energy district, of course, but another very important aspect of district operation is, of course, the greenhouse gas emission balance. So this diagram shows how many kilograms of CO2 equivalents are emitted by the building operation and mobility per square meter and year. And here you can see the very large difference between the fossil solution with natural gas as compared to a district heating system, which is assumed to be the Viennese district heating that uses a lot of waste incineration and other forms of renewable, quotation marks, energy source with a relatively low CO2 emission factor. But the heat pumps, even though they're using Austrian power grid with the emission intensity of the power grid is lower than that, and using flexibility with that is even further decreasing the greenhouse gas emissions. And this is because when we're flexibly using the grid, we're using renewable overshoots, renewable peaks, which actually have a greenhouse gas emission factor of 0 assumed in our assumption. So this means that increasing the flexibility also decreases the greenhouse gas emissions. And these effects can be even higher if you have other grid greenhouse gas intensities.